So all of the examples that we've done so far, which is all two of them, the role of the top function and the role of the bottom function stayed the same throughout the region of integration. So in this picture, you can see these graphs never cross in our region of integration. In this picture, you can see these graphs cross, but we want to find the area bounded from above by this curve and below by this curve. So we're not really worried about the part beyond where they cross. But the next thing that we want to look at here is we want to look at a situation like this, where our region of integration is A to B, but the two graphs cross at some point. Okay. And basically what we're doing is we want to make sure that this area here and this area here are both counted as positive area. So I can't just do a straight subtraction, because if I did a straight subtraction, this area would be positive, but then this area would be negative. And the way that I get around that is I do what I did when I found the total area. That is to say, I calculate the absolute value of the difference between the two functions. Now, all this does is the net effect of this is it makes sure that the top function is the top function and the bottom function is the bottom function. So instead of just subtracting the two things in general, when I put the absolute value there, we can split it up part way where they cross. And because f is bigger here, I put f in front on the interval from A to C. From C to B, the role of the top function changes. So I'm going to put the g of x in front first and then subtract the f. And we're going to add these two because this is the sum of two areas. Does that make sense to everybody? So you don't really need to mess with the definition of the absolute value. I wanted to emphasize that because multiplying by -1 is what allows us to interchange the f and the g for the second integral over here. But as long as the top function is always on top, always first, and you're subtracting the bottom function away, you're good. All right. So so if you were to look at this integral over here, first of all, there's a typo. This should be a plus. Thank you for Terry for pointing that out to me. But this picture is a good example of the situation that I'm talking about. So what we're doing is we have two curves. We have cosine and we have sine, and the region of integration is from 0 to pi. And you can see that they cross at pi over 4. We figured that out by setting the two equal to each other and solving. So once we know that it switches at pi over 4, we have the top function, cosine is the top function, and sine is the bottom function. That's from the region from 0 to pi over 4. And then at pi over 4, it switches. And then sine becomes the top function and cosine becomes the bottom function. So that's why we have sine here and cosine there. Okay. Once you have this set up, you can just find the antiderivative and plug in the points. So that's this example is just to try to set it up. Was there any questions about example 3? No questions. Okay. So let's take a look at example 4 together. I want to draw a picture and really ask you a couple questions. So in example 4, it says, if R is the region between the graphs of the functions f of x equal to x squared and g of x equal to 2 minus x and y equal to 0, we want to find the area of the region that's bounded by these three functions. So these three functions are going to act like a boundary. So let's try to graph this real quick. So let me put a y-axis here. And let's put a x-axis over here. And let's label this. We got 0, we got 1, we got 2, we got 1, 2, 3, 4. Here's -1. Here's -2. Let's do our f of x in blue. So I can graph x squared pretty easily. These dots will just be guidelines. Comes up like this. This guy comes up like this. And this is our curve. This is our f of x equal to x squared curve. When I look at my g of x curve, I immediately recognize that this is a line. The slope is -1, so it's going to be going down like this. And the y-intercept is 2. So we could label 2 here like this. And let's do this in green. Something like this. Maybe make this go a little bit. Oh, maybe make this go a little bit further. Like this. Okay. And then the final curve I have is I have y equal to 0. And y equal to 0 looks like this. Let's do this one in purple. It's y equal to 0. This is y equal to 2 minus x. Whoops. 2 minus, whoops, 2 minus x. And the blue one is y equal to x squared. So I have a question for you all. Do you all think that the region we're looking for is 1? Oops. Do you think the region that we're looking for is this area right here, which is 1? I call that guy 1. Or do you think the region that we're looking for is this? Let's call that 2. Anyone have any thoughts? Two people have thoughts. They message me privately. What about the rest of you? What do you think? Oh, Ken says publicly too. Okay. So why do I make a big deal about this? I've asked this question before, and I think it's because, we look at earlier examples like this example 2. Sometimes students just jump to the conclusion that we're looking for this region right here. But that's not the case. We have 3 functions, so we're looking for the region bounded by all 3. So that would be 2, not 1. Okay, so I'm hoping that if I draw attention to it now, then we won't make a mistake on it later when we take a quiz. But this is what we're looking for, so I'm going to shade it in. This is the region that we want. All right. So step 1 was to just sketch the situation. The next thing we got to do is we got to find the intersection points. So I can really, I guess first thing I could do is I can find this point right here. And if I find this point right here, that'll tell me where or let me back up a sec. What's interesting about this problem? Well, I hope we can all see that the region of integration is going to be from 0 to 2. That's that's because I drew a decent looking graph. We can find it algebraically as well. How can we find it algebraically? I can set the y equal to 0 equation equal to the green graph. And when I set these two equal to each other, what value of x is going to make this guy equal to 0? X has to be 2. So that's one way you can see that that point is 2. How do I find this picture? I set x squared equal to 0. When you set x squared equal to 0, that makes x equal to 2. So I know that my region of integration should be from 0 to 2. So what's the problem? Can someone articulate the problem to me? Any thoughts as to why this is an interesting question? Maybe it's too obvious. I think what makes this question interesting is that the top function changes partway through. The top function is the blue function at first, and then it switches to the green function next. So we really want to figure out what's the x value of the points where those guys flip. Okay. So let's find some intersection points. If I set 2 minus x equal to 0, this tells me x equal to 2. If I set x squared equal to 0, this tells me x is equal to 0. So this is my overall region of integration. It's going to be from 0 to 2. But because the role of my top function changes at some point in the middle, I need to figure out what that point is. And the way I find that is I set the other two equations equal to each other. So I'm going to have x squared equal to 2 minus x. And this will help me find out what this x value is. So let me solve that. So I'm going to move everything over to one side. I'm going to get x squared plus x minus 2 is equal to 0. And this means that 0 is equal to x plus 1, x minus, or x minus 1, sorry, x plus 2. Okay. Which tells us that our intersection points are going to be -1, I'm sorry, -2 and 1. This is x equal to -2 and 1. If you look at the x equal to -2 part, that's this intersection point. We don't care about that one. So we don't care about that. But the part that we do care about is this point here when x is equal to 1. So that's the one we're going to use. Is there any questions so far? You can always ask. No questions. Okay. This is my quietest class, but it's also the class that's kind of doing the best. So I don't know what that means. As long as you do well, I guess I don't really care. But I want you to feel free to ask questions, obviously, if you have questions. Now we can set up our integral, right? So when we set up our integral, we're first going to go from 0 to 1. The top function in that case is going to be x squared. And the bottom function is just going to be 0. And then for the second part, I'm going to go from 1 to 2. The top function is now going to be 2 minus x. Bottom function is still 0. Did I need to write these zeros here? No. But it doesn't hurt me. Okay. And then I just integrate each piece. So this guy is going to be the antiderivative of x squared is x cubed over 3. I'm going to go from 0 to 1. The antiderivative of the second piece is going to be 2x minus x squared over 2. I'm going to go from 1 to 2 like this. And then I get 1/3 minus 0 plus, I'm going to get 4 minus 2 minus 2 minus 1/2. So when we simplify this down, you get some number. What number do we get here? We're going to get 1/3 plus 1/2. I think that's going to give us 5/6 units squared. That'd be our final answer.